So what we will do is talk about multiple source files. We can write programs using a single C source file, but that only works in simple cases. Because putting everything in a single C file has the problems of turning the compilation slow, making several people working in the same program very difficult, and it makes difficult to reuse code. So we should separate code in several source files, where every set of files represents a logical entity, what we call a module. It can be for handling a timer, handling the word, handling the analog to digital converter, etc. In a way that models can be compiled separately and the code can be easily reused. And in this way, different programmers can work in parallel in different models. So the logic of using models is this one. Let's suppose that I have a program called A that uses the analog to digital converter. And I have created a set of elements, which we know that are called modules, that have been developed to work with the analog to digital converter. I have this analog model, and also I have other peripherals, and I have developed other models to work with the output compare model to generate PWM, with the timer to control the timers, etc. If I have done this, and this is a separate block that I can separate from the rest of the program. If another program also uses the analog to digital converter, I just need to include that model in the other program. So I can reuse code. Once you write code for the analog to digital converter, you don't have to rewrite it in other programs that you develop. So the condition is that this analog must be easily movable from one program to another. And also each model can have a small test program. And in this way, I can test each of these models separately and guarantee that they are working, and only then including them in the main file. Now we're going to see how do we work with multiple source files. Now let's suppose that I have a function that I want to, that could be the function that handles the analog to digital converter, for instance, and I want this to be compiled separately. I have a C file with this code, and I want to test this. I can do it with the code that you have. I'm going back to the root. If I write git checkout and I press tab again, I can see all the possible options. In this case, I forgot. I will have to add. I should have that mentioned in this slide. That is not here. I will add that afterwards. I want to use this version. That's where these files for this example are stored. I have it now, and I have here the file part1.c, the one you see here. If I try to compile using this command, sorry, if I try to compile using the command there, gcc it will issue an error. Why? Because every C program requires a main function. That's where the program execution starts. So this is not a program. This is part of a program. This could be a model. So what I want is have an application that uses the function. In this case, F1. So this application uses two functions, F1 and F2. F2 is defined in the file f1.c, and F1 is defined in another file. So I want to create an application which I can call app1. And then what is necessary for this application? We need to have the main application source file, app1.c, and we need to have the file that contains the function F1. So remember that each of these will, app1.c and part1.c, will create an object file, and that object file will be linked into a single program called app1. So if you do this, we get an error, not an error, a warning, that there is an implicit declaration of function F1. But I still have an application to run. And as a matter of fact, it works. Okay, the main is simply calling F1 and then calling F2 and terminating. I have here the result of calling F1 and then calling F2, and then the program terminates. We still have a warning, but we will see how to solve it. Okay, now let's see one solution that a lot of people do, which is to include part1.c. So I'm going to include the C file. I can edit the app1c file, and I can add that to solve the problem. Now, one question. Notice that I'm writing this kind of signal and not the greater than and less than. What is the difference between one symbol and the other symbol?
One is a file, the other is a library.
It's close to that. This one, yes?
Part1c was created by you as
The first line means to look for this file in all the system folders. That's where libraries are, etc., etc. So when it's a system library, I need to use this kind of signs. The second option means search this file in the project folders. So it's not a system file, it's a user file. If I write it like this, let's try to compile the program now. So I don't have part1, I just need the app1. Okay, I get a fatal error. It doesn't find, it's unable to find part1.c. Why?
Is it because they're compiled at the same time, so the other one is not available yet? I don't know.
The problem is that I'm using less than and greater than, which means that this is an instruction for the compiler to look for this file in the system folders. There is no such file, and then he comes back to us saying there is no such file or directory in the system folder.
So whenever we are creating a file in which we will look for the variables and everything, we should use quotes.
We should use quotes for your files.
Yeah.
Files that are in the same folders as in the, or in the same system of folders as the source file. The compiler will look for them in the same place. When you include library, the headers from library files, you should use the greater than and less than, because these are the signs indicating that look for these files in the system folders. Now, if I have part1 as a local file, okay, this compiles and works. Now, an important thing that we will see further on. This thing works, but this is the wrong way of doing things, okay? The compiler accepts it, doesn't issue any error. In what concerns correctness of C language, this is syntactically correct. There is no problem with that. And this is an excuse that people use to do things this way and then say, but it compiles, no errors, it's okay. No, it's not okay, because you can write totally perfect, totally grammatically perfect text, and that's still nonsense. Okay, but the grammar can be totally correct, but we will see why this is not this is not right. So one of the things that we need for multiple source file projects is function prototypes. Why is the reason when I had the first version, which is this one, and I try to compile all the pieces together, I have this this warning: implicit declaration of function F1. Why does this happen?
Well, because the function was not declared before main.
And why do we need the function to be declared before main?
So as to, I don't know how to explain it very well, but it's like main should look for the function name before it happens inside its own call. So if you try to call function F1 inside main without ever referring to it or declaring it, it's like trying to access a variable that does not exist yet. So you have to declare first the variable to use it. It's more or less the same thing, a bit more complex. I think you cannot use function F1 before declaring its name.
Okay, it's similar, but it's not the same, because there's a difference in the two situations.
Yeah,
If I use a function and I don't declare it, I get an error and the compilation stops. I won't have a running program. But in this case, it issues a warning, but it still gets to solve things. And the question is, why do we need to, let's say, to talk about the function before it is used? Recall.
Maybe it
yes.
has something to do with the compiler.
Yes.
I don't really know it uh, very very well, but I think it has to do with the compiler knowing there is function f1 somewhere and then looking for it in the other files and linking it to the main file.
Yeah, linking will occur. It has to do with linking, but the issue is the following. It's not actually the name of the function, because the compiler can live with it, as we have seen. Okay, I've seen this. No one has introduced it to me. And notice an important part of the message: implicit function declaration. So the compiler will say, no one has introduced this to me. I will assume something, right? And how does the C compiler works for calling a function? Do you recall that?
No, sorry.
Who remembers what they have talked about in computer architecture 2? That was about two years ago. How does the C compiler works when we are calling a function? The main will call a function. What does the main need to do for a general function? Functions usually have what?
Input arguments
Input
and output
arguments.
arguments.
Okay, so what does main need to do with the input arguments?
Well, it
Yes.
has to pass to function f1 or whatever those input arguments, either by reference if we're accessing it externally, or directly if they are in the same file.
Okay, let's suppose it's passing by value. What does what mains need to do? The compiler will need to store the input arguments somewhere. Okay, and they are stored one after the other. And then functions, not in this case, this is a void function, but functions often return values, right? And these values are also stored somewhere, right? So imagine a function that takes two arguments and produces one output result. These two arguments can be char. A char takes 1 byte. So the two arguments and the result, they occupy 3 bytes. But if instead of being chars, they are short ints may have 2 bytes. So now we're talking not about 3, but 6 bytes. If they are int, they may take 4 bytes each of them. Now we are not talking about 3 or 6, we are talking about 12 bytes to store the input arguments and then getting back the results. So the problem is that when I call a function like in the way it's shown here, with no previous announcement, the compiler has no idea whether this will return a value or not. And if it returns a value, is it an integer? Is it a 32-bit value, 16-bit value? And also, does it take arguments? Is it really like this? Did the user forget to write the input arguments? The computer has no clue, the compiler has no clue about what happens. That's why we need to have the declarations before. The problem is that compiler will assume, usually it assumes that it returns an int, but that may generate problems as we see in the following. So for instance, if I have this example here, x receives the value from a function multiply two values. Are these chars integers, long, sine, and sine? And this means, as we have seen, a lot of difference in the memory space and in the place where these things will be stored and where main needs to look for the result at the end. So if I just show this for the first time, the compiler doesn't know what to do. It will guess the best it can. If I show this previously, now the compiler knows this is an integer, this is an integer. It will produce an integer as a result. So that's why we use header files. So the idea of header files is for files that have functions defined on it. I have header files with what's called the function prototypes, defining what kind of function it is. So each file with a name.c should have a header called name.h. And this will contain the function prototypes. And all the other programs and models that use the functions implemented in this name.c, they must include name.h. So the conventions are .c never contains function prototypes, .h never contains implementation, only declaration. So .c is for implementation, .h is for declarations, and a rule of thumb, never include .c files. So if you do that on this example, what I'm missing is this part1.h file. And in this way, part1.c and part1.h, they are a module. And now this is what was missing in the previous slide. You have here a tag called mef OK, and this is used when if you want to practice this at home. This example corresponds to the tag mef_OK. So what I need to do is git checkout and then write the tag to the corresponding point. Now, if you if you find this kind of errors, that's because I have made changes to a file and it does not allow me to overwrite that file. As we are working with an example, one thing I can do is this command, which is reset what I have and forget about all the changes I've made. So I get a clean version of the repo, and I can check out the version that I want. Okay, now I have the app1 file. So I have the application file, the code for the module, and the header for the model. And if I try to compile, I want to generate a file called app1, and I want to compile the main source file and the model source file. Note that I only include .c files in this command, no h files. They are included in the source files. And at this moment, I get no errors, and I have an application ready. Okay, I can sophisticate this. So you have several examples of, before going on, several examples of how to do this and how to compile C files or organized in models. I can do what I've just done, compile everything in just one step, or I can compile each of them separately. I can compile, I have two C files here, and if I have a properly working program, I should be able to only compile app1.c separately. It should produce no errors. Now let's add all the possible warnings. No problems. I can try that with part1.c. Functioning, no problems. And now I can build one application. I have now two object files, and I can build my application from the two object files. In this way, the GCC will only call the linker, and it will not need to compile the file. One way to verify that I have a correctly working program or module is that I can compile it separately. In this case, part one is a correct model, at least syntactically. When this happens, I compile and I get no errors. Now we will have you have also a tag called MEF improved, which is multiple files and a slightly improved function, which is the use of this structure. When I have the same header file, that header file can be included several times. And that means that the same function would be defined several times, and that would create problems. So what we do usually is to have a structure like this. This is a preprocessor command, and it means that if this tag called name _h, in this case, name would be the name of the file. If it's not defined, then execute this. Define, I write all the contents of the file here, and then I terminate with endif. What do we get with this? First time that the file is included, this name is not defined, and so this is true, and I will run this. One of the things is define the name. On the second turn, when the compiler gets here, it will see name defined, so this is not true, and it will skip the whole contents of the file. And in this way, I guarantee that I just have one single inclusion of the file, even if I have several commands for including the same file. So the tag is MEF improved. Now I checked out that version. If I open the part1.h file, you see the structure here. I have this definition only if it's not defined, and if it's already defined, it will skip the whole file. And so this is the basics of C and H file in inclusion, and we will have a look at how to do that in the lab classes.